Welcome Year 11 Advanced Maths students to another exciting class with probability distribution functions being our focus. Today we're going to be looking at a thing called expected value. So let's go through the theory behind it first and do some examples. So the first thing I want to do is I want to consider flipping 4 coins and just counting how many tails you've got. Now remember, in the past we could have done that like this. We could have gone, you got heads, tails, and then you got heads, tails, and then you got heads, tails, and you got that sort of thing, and you got that one, and when you finish, and we'll keep going, you would have ended up with heads, 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 or heads, 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 tails, or heads, heads, tails, heads, and you go through all of the different possible combinations. And with 4 coins, there's 2 to the power of 4, which is 16 different ways you could end up with answers. So that's what we're focusing on. So let's break that down and look at this now. This table here talks about the number of tails you get when you flip 4 coins. So what's the probability of getting 0 tails? Well, if you followed your tree diagram through, there is only one way out of the 16 different outcomes where you get 0 tails. In other words, you got 4 heads. If you look at your tree diagram and you said, what's the probability of getting 1 tail? Well, there would be 4 paths, and they would have been the options where you had tail, head, head, head. You would have had head, tail, head, 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 tail, head, 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 tail. And they're the 4 different ways you can get 1 tail. So 4 different ways of getting 1 tail. What's the probability of getting 2 tails? Follow it, you get 6 ways out of the 16. 3 tails, 4 ways out of the 16. 4 tails, 1 way out of 16. And if I add this row up, 1 plus 4 is 5, 11, 15, you get 16 out of 16, which adds up to 1, which means I've included everything. Now, instead of writing this P of x equals x, that means the probability of capital X equals little x is your number of tails, capital X is what you're looking for, so the probability of getting 0 tails, or getting 1 tail, or getting 2 tails, that's what it implies. It's a messy way of writing it, so we abbreviate that with a little p of x, saying that's the probability of getting what you're looking for. So this table here and this table here are identical. They're both talking about the number of tails you get when you flip 4 coins, but the only difference is the language here, talking about capital P for probability. Little p means the probability of x occurring. X is each of these particular values. So let's talk about expected value. Before we do, we know about the concept of the mean or the average. To get a mean or an average, you add up the number of, add up how many numbers you've got and divide by how many you have. So here's an example. If I have 2, 4, 7, 8, and 9, and I want to find the average or the mean of that, I add up the numbers and divide by 5 because there's 5 numbers. In this case, I get 30 over 5, which is 6. But there is a different way I could look at that. I could say the average or the mean is, because there are 5 numbers and there's 1/5 of a chance of each number happening, if I sort of think of it like that, I could say I could do 2 times 1/5 plus 4 times 1/5 plus 7 times 1/5, and so on. Get all the fractions, add them up, they add up to 30 out of 5, which is 6. You could actually think of that as having a common factor of 1/5, and if you took out the common factor of 1/5, there it is there. Everything is commonly divided by 5. That's what 1/5 is, dividing by 5. Now, it's a weird way to look at it, but when you're dealing with probability, you can't treat it like an average. If I want to find a thing, I need to, well, if I want to find an average, I shouldn't say a thing, if I want to find an average or a mean of a probability distribution that's discrete, I need to talk about a weighted mean, and the weighted mean is going to come based on the probability of something happening. So let's go back to our toss 4 coins scenario. If I flip 4 coins and I said, what would I expect to actually happen? Would I expect to get 0 tails, 1 tail, 2 tails? Let me just go back. Here's our table. If I flip my 4 coins, what would I expect to happen? Well, looking at this, I'm going to have a better chance of getting 2 tails than I am of getting anything else. And because it's nice and symmetrical, I'm expecting my answer would be I've got the best chance of getting 2 tails when I flip my 4 coins, 2 tails, 2 heads. That's what I would expect to happen on average. But doesn't mean it's going to. That's just what I might expect if I had to look at that. So let's come back here. If we use the formula, we'd say 0 tails happens 1/16 of the time. 1 tail happens 4/16 of the time. 2 tails, 6/16 of the time. 3 tails, 4/16 of the time. 4 tails, 1/16 of the time. Figure all of those out, put it into your calculator, you get 2. So this weighted mean is called an expected value of X. An expected value when you're dealing with flipping 4 coins, and we would expect to get 2 tails. Here's our formula that we're going to use to find the expected value. Now it looks quite complicated. Remember that sigma means sum. X means what you're looking for. P of X means the probability. So we'll do some examples and that'll make sense in a moment. Sometimes we also use the letter mu. It's a Greek letter, there it is there, to say mean, just so that you're aware of that. Now, the expected value of a uniform distribution. In a uniform distribution, all the values have the same probability. So that might be something like rolling a die. And what number have you got? You got the same probability of getting a 1 compared to a 2 compared to a 3. They're all 1/6 for each of the numbers on a die. So we'll deal with a expected value of a uniform distribution in one of the examples in a moment. So let's look at our examples now. Here's the first example. 20 friends go out to dinner at a Vietnamese restaurant. 1 has $460 cash, 3 have got $370 cash, 2 have got $150 cash, 4 have $90 cash, 3 have $60 cash, 2 have $50, 5 have got no cash and they're expecting to scam off their friends, borrow from them. An armed robber bursts in and seizes one of the friends at random. She threatens him, grabs all his cash, and then runs away. Let X be the amount the criminal seizes. Complete the probability distribution table. So these are the options. The criminal could seize no money if they randomly pick one of the people with no cash. The criminal could seize $50 if they randomly choose one of the people with $50 cash, and so on. So they could choose people with any one of these amounts of money. Well, what's the probability that the criminal would pick someone with no dollars worth of cash? Well, we know that 5 people have no cash, and we know there are 20 people there. So 5 chances out of 20 of picking someone with no money. How many people have $50? $50, 2 people have $50, so there's 2 chances out of 20 of picking someone with $50. And when you go and look through the rest of them, $60, there are 3 people out of 20 with $60. $90, 4 people have $90, so there's 4 chances out of 20. $150, 2 people, so there's 2 chances out of 20. $370, 3 people, so 3 chances out of 20. $460, there's only 1 person with $460 cash. If I add all of those up, they should add up to 20 out of 20, which is 1. If they don't add up to 1, we've got a problem because we haven't taken into account all of the scenarios. Now, this row is X multiplied by P of X. So you take the X value and times it by the probability of that occurring. So $0, you got 5 chances out of 20 of getting someone with $0. We times those two together and we get 0. For the next one, $50, you got 2 chances out of 20 of getting a $50 person. $50 times 2 out of 20 will cancel down to 5. The next one, 60 times 3 on 20 gives 9. 90 times 4 on 20 gives 18. 150 times 2 on 20 gives 15. 370 times 3 on 20 gives 55.5. And 460 times 1 on 20 gives 23. Now if I add every number in this row up, they add up to 125.5. So that's finished my table. I've completed the distribution table like I was asked to do. Next thing I've got to do is graph the distribution and then state the expected criminal gain. So let's graph the distribution. Well, I have an x and a p of x. So I'm going to have x and p of x. Now p of x, when I look at p of x, the numbers go from 1 on 20 all the way up to 5 on 20. So that's 1 on 20, 2 on 20, 3 on 20, 4 on 20, 5 on 20. Bit hard with my pen to fit that in, so hopefully you understand what I've done there. Now, money-wise, I'm going out to $460. So I might go, that's like $100, $200, $300, $400, $500. So $0, yep, $50 would be there. Next one is $60 on my scale, that would be about there. 90 would be about there. Next one's 150, so that would be about there. 370, there's 200, 300, 370 would be around about there. And 460, I'll say, is about there. So that's my money. I now need to graph the distribution. It says graph it. Well, there's my set of scales. Let's graph it. $0 happens 5 out of 20 times. $50 happens 2 out of 20 times. $60, 3 out of 20 times. $90, 4 out of 20 times. $150, 2 out of 20 times. $370, 3 out of 20 times. And $460, 1 out of 20 times. So you can see from the dots sort of how high and low. The higher the dot, the more chance there is of that scenario occurring. Now the last thing it says, to state her expected criminal gain. If I actually write the formula, the expected criminal gain, or the expected amount of money, is going to be sigma x p of x. What does that mean? It means add up or find the sum of the x times p of x values. I've already done that. Here's the x p of x row, and I've summed it. If I've already done that, that means the expected value that this criminal is going to take home is $125.50. So if the criminal comes in, all the friends are at the table and have this cash, and they randomly pick one person to rob, we'd expect, as an average, a weighted mean, the expected amount we could say that they might take off with is $125.50. Let's try our second one. Now, our second one is an example of the expected value of a uniform distribution, because things have equal chances. So let's actually have a look at what's going on with question 2. A die is thrown. graph the distribution and find its expected value. Well, when we throw the die, we can get a 1. Oops, that's changed. We can get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Now, P of x means what's the probability? What's the probability of getting a 1? Well, I've got 1 chance in 6. P of x for number 2. What's the probability of getting a 2? 1 chance in 6. Chances of getting a 3 and a 4 and a 5 and a 6 are all 1 chance in 6. If I add that row up, it adds to 6 out of 6, which is 1, which is what I want. Now I have to look at this, x times P of x. 1 times 1/6 is 1/6. 2 times 1/6, 2/6. 3 times 1/6, 3/6. So I'm multiplying, 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 and writing the answers underneath. 4 times 1/6, 4/6. 5 times 1/6, 5/6. 6 times 1/6, 6/6. If I add this row up, 1 and 2 are 3, 3 and 3 are 6, 6 and 4 are 10, plus 5, 15, plus 6, 21, I get 21 over 6. And 21 over 6 is, as a decimal, 3.5. Now, the question says, graph the distribution. So, graphing the distribution, I have an x-axis and a probability axis. Now, when I look at all my probabilities, they're all the same. They're all 1/6, so I can just go here and go 1/6. When I roll a die, I can get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And the probability for each roll is the same. It's uniform. So there's my graph of the distribution. The question also says to find the expected value. So what would you expect to roll? So if we're rolling a die, on average, we're treating this as like an average, we would expect to get the sum of each outcome multiplied by its probability, and I've already done that. I've got an x times P of x row, and I've summed it, so I would expect to roll a 3.5. It's purely statistical. That's what you would expect. Right, time for you to enjoy the experience of working through exercise 13b. Have fun. Bye for now.